Good morning. 안녕하세요. 네, 안녕하세요. Good morning. Okay, I think we can get started.
The target modality is
All right, let me just mute everybody first, just in case. All right, so welcome to week 4 of AI504, and today we're going to talk about autoencoders. But before getting into the material, so I just want to confirm that all of you have watched week 2 and week 3 videos and lecture slides. So week 2 was machine learning theory. Well, not theory, but like machine learning basics. So there were like, we covered what it means to have an objective function or loss function and how to optimize it using gradient descent. And we covered some, like series of like well-known algorithms. And thankful, I mean, we because of due to the international travel, I couldn't do the theory session, but we could thankfully do the practice session. So that was week 2. Week 3 was a little bit more serious. So week 3 was going from logistic regression to multi-layer perception, and then talking about backpropagation algorithm and how programs, I mean libraries such as PyTorch can help you do backpropagation automatically. We call it autograd, right? So and because of Chuseok, the holidays, we couldn't have the theory session again, which is unfortunate. But we also thankfully could do the practice session. So I am a little bit concerned, as I said in the KLMS, that we're missing 2 consecutive theory sessions, which are kind of like crucial for understanding all that is to come afterwards from today and onwards. So basically, those are the basic, like foundational, fundamental knowledge. And I'm hoping that everybody has covered their ground by watching the lecture videos that I shared on KLMS. But if you have any question, you can ask them now. Like if you have any question regarding week 2 and week 3, now is the time. I said on KLMS that I would have a Q&A session on 9 p.m. on those like previous week and the week before that, but I didn't see anybody come. Actually, like there were only two people showed up on the first Q&A session, and it wasn't about the class material. And the second Q&A session, nobody showed up. So I hope that's a good sign. But if you still have any question, you can ask them now. 혹시 질문 있으실까요? 위 2랑 위 3에 대해서. 난 뭐 이해가 잘 안 간다. 아니면은 이미 이제 LLM하고 얘기를 해봤는데 잘 뭐 대답을 안 해주더라. 이런 게 있으면은 지금 질문해 주시는 게 좋을 것 같습니다. 네, 질문이 없으신가 보네요. Okay, so if there are no questions, then we can move on to today's material. Oh, by the way, I also was wondering how is what it's like for your what it's like with your experience with the LLM, the one that we made with the link chain, is that helpful? Does it answer your question very well, or is it just, have you been using it so far often? Very helpful. That's good. That's good. So you're asking all the questions to the LLM, and it's like, is it related to like operational questions, or has anybody asked a question to the LLM regarding the class material, like class two or like lecture two or lecture three, like anything theoretical you didn't understand, and you asked the LLM about it, and then it gave you like a helpful answer? Not right now, but I think I will. Sure, okay. I've asked about the contents of assignment that knows quite well about it. Okay, sure. I mean, there were only on one assignment regarding the like installing Anaconda locally, but I think it does well in explaining the contents in a simplified manner. Okay, cool, cool. Yeah, so I'm asking because unlike last year when there was a lot of questions on the board, like class and board, I don't see any question on Calamus except for someone asking something about class lecture four. I mean, week four, way in advance than week two. So besides that, I didn't see any question. So I'm hoping that is the sign of the LLM helping you guys out because there were a lot of questions last year. Okay, so I think we can get on with the material then. So today's topic is we're first going to talk about latent representation. Oh, what? So, latent representation, and then we're going to get into the autoencoders, and we're going to go a little bit about the high level overview about the training process. I guess a lot of people are already familiar with the training process, but um, if we have time, we're going to cover some ground. And then visualization, how we can visualize the embeddings that are embedded in the latent space. So we're going to see how we can do that. And then if we have extra time, we can talk about some autoencoder variants, such as denoising autoencoder and sparse autoencoder. Oh, Neha. Yeah, LLM is helpful. Okay, cool. That's good to hear. I'm thinking that it'll be actually more helpful than human TAs because it's always there. It can answer your question right away. It doesn't take, you don't have to like wait for the emails to come, like the TAs to respond to your email. You don't have to do any of that, right? It's always there. It can always answer your question. And I think the accuracy was pretty high because the questions are not super complex. You're asking like facts, like piece of like information, a piece of like facts from the class. So I think that is a bit a lightweight load on the LLM side. So yeah. All right. Let's get on with it. So latent representation. So Namho, is there a metric on how much it could hallucinate? Not really. We didn't like stress test how often it hallucinates, but based on our experience with the TA and myself, I didn't see any hallucination actually. We've interacted it we've interacted with it more than probably 100 times, but I didn't see any hallucination. But it can forget to include some very like minor details because like what we do is we provide it with the audio transcription of the lectures, and also we provide the slides based on how we first extract textual information from the slides, and then we provide it. So uh, it's a lot of material basically, and based on the retrieval augmented generation, it might sometimes forget to include like very minor details, but that's it. But you should always be careful. You should always be aware that sometimes there's a very small chance that it will hallucinate. So, don't take its for it like all blindly. Right, so latent representation. So we've covered, hopefully everybody's familiar with this this figure here. So what that was a multi-layer perceptron where you put a pixel information into the input layer, which this is the input layer, and then you have a four-dimensional hidden layer. We're going to call it a latent layer or hidden layer here, and then based on the representation in the four-dimensional latent space, you have a final prediction. So as I said, this is a chain of logistic regression. You can see this as a single logistic regression if we're using here a nonlinear activation, the sigmoid function. And then obviously this again is a logistic regression because this is a binary classification and you usually use sigmoid function here again. So it's a chain of logistic regression. And the second layer here, this layer is a logistic regression based on four features, four hidden features. We don't exactly know the meaning of each dimension here, but we assume that it might be something like this because the objective function is to classify the given image into a man or a woman, and probably the latent representation or the latent space, each dimension is probably learns something that is useful for predicting or classifying whether this image is a man or a woman. So something like, does the image have a long hair, or does it have a mustache? Does it have ribbon? Does it have makeup? Something akin to this. So we've assumed that, the latent representation might be, it's not 100% interpretable, but it might be something like this. Yeah, it's a four-dimensional latent representation vector for the given image. So you can assume that this was 784. So if we assume that this is a 28 by 28 dimension pixel image, and then your input space will be 784, but you're compressing it to four-dimensional space, right? So now your image is just four-dimensional. It has lost most of its information, most of the like granular pixel level information, and it only retains the high level, very high level information that is helpful for the model to classify whether it's a man or a woman. And obviously, each image will be transformed or compressed into a different kinds of four-dimensional latent four-dimensional embedding. So this would be transformed into this would be transformed into this because she has a long hair. She doesn't have a mustache. So she has a long hair, so it could be 0.8. Doesn't have a mustache, so 0.1. Ribbon, is like a tassel or something. So like high score on there and there's no. But Alan Turing has none of that. So it's all 0.1, 0.2, 0.1, 0.1. So it'll most likely be classified to man. This will be most classified to a woman, right? So that's how it goes. And obviously, each element in the set of the original space. So the original space is 784 dimensional space. So we can think of it as a set. So it's an infinite element set where each element can be any image in this space, right? So it could be this person, like, like there are infinite number of elements in this set. And it's not just human like faces. It could be just completely white image, completely black image, completely gray image. It could be anything, right? And all those individual elements will be mapped to one embedding in this four-dimensional space, the compressed space. So, like Kim Jong-un would be mapped to where? Like here, and Yona Kim would be mapped here, and each would have different numbers, different values in the four-dimensional space. So we're just basically what we've done is based on using this layer here, you're compressing this set into this set, right? So obviously sometimes like similar looking images could be mapped to the same place. I don't think I drew it here. Yeah, for example, like this and this happens to be mapped to, the same value. But I mean, this is just an example. I mean, it rarely would happen because this is a real valued space. So no two images in this space will be mapped exactly to the same, the same spot in the four-dimensional space. But if you have like, if you're using like low bit low bit representation, then sometimes it might happen. If you're using like 4-bit or 2-bit floating points, then sometimes that might happen. Anyway, so in this latent space, this hopefully, I mean, we could imagine each axis of these 4-dimensional space would be responsible for like these high level semantics, like long hair, mustache, or ribbon, or makeup. So like this first axis could be long hair axis, this could be mustache axis, this could be a ribbon axis, then there would be like makeup axis, like somewhere I can't draw because this is a 3-dimension. This has to be 4 dimensions. So, and like this particular instance would be like somewhere here, like it's hard to draw it. If it's here, it would be like here, something like here, something like that. So they're basically living in this 4-dimensional space. And how did we learn this space? So this is where the importance of the latent space comes in. So how did we learn this space? And basically what we did is we simply just trained this layer by backpropagation. So the end goal is to classify this image into a man or woman. So all the parameters here, they're all tuned, or like they're optimized towards minimizing the cross-entropy error, or the negative log likelihood error of this entire model for doing this job. So your latent space will be shaped in order to maximize the performance of these models to perform man or woman classifier, right? So that's what it's saying here. By minimizing the cross-entropy loss. This is the only objective, only criteria for learning your latent space, the 4-dimensional, the 4-dimensional space, and nothing else. You're not using any other objective function, right? You're using only the cross-entropy function. So that's the only like, like guidance given to shaping this latent space. And I'd like to actually show you this, how latent space can be shaped, because this is very helpful for understanding how deep learning models are trained. So give me just a second. Let me fire up the website. All right, so this is a very helpful website. So I've included that in the slide. So if you want to revisit the site, you can do it later. So this is a very helpful slide that I myself used to understand the latent space, and it's very old. It's like from 2014. So it's like in the era of the beginning of deep learning, So here we have, let's for example say that we have a binary classification problem, and there are 2 classes. So this is the blue class here and the red class here. So, and you want to classify it. You want to draw a boundary line here, right? So let me see if I can annotate, right? So you want to somehow classify it like this, but that wouldn't be linear. Let's assume that all you have is a linear classifier. So you just have to draw a linear line like this. Like this is the best you can do, or here, or you can draw it like this. But always, in any case, there will be some error, because, for example, if this is the line you drew, then you are missing this part. You're misclassifying this part. If you drew a line like this, then you are misclassifying this part, right? So you can't perfectly classify these 2 classes with a linear classifier. So that's a problem. So yeah, you can see that this is the best we can do. So a little bit of error here, a little bit of error here, and a little bit of error here, but there's still error, right? And in this case, what you can do is you can actually add a hidden layer to convert your model to a nonlinear classifier. So if you just use like logistic regression, then this is the best you can do. This linear decision boundary is the best you can do with a linear classifier. But if you use multi-layer perceptron with like 1 or 2 hidden layers, let's go with the one hidden layer example. Then you can start drawing a non-linear decision boundary. So if you have a hidden layer like this here, then you can start drawing a non-linear decision boundary like this, and then you can have a perfect classification. There is no error here, right? So that's the power of adding a hidden layer into your model so that you can draw a non-linear decision boundary. But what really happens is if you look at this part, well, actually, there should be only one like node out there because this is a binary classification. So you can just have a sigmoid function here, and then it'll just give you a decision boundary. So you don't need actually two outputs just because you're having a binary classification. Only one output suffices. But anyway, so let's assume that you have just one output. So it's like this. Like this, right? So here in this second logistic regression, I said that a multi-layer perceptron is just a chain of logistic regressions, right? So in the second logistic regression, this is a linear classifier, right? In the entire in the whole picture, in this entirety, this is a non-linear classifier. But in the second layer, second logistic regression, this is still a logistic regression, right? This being the input, this is the input to the second logistic regression, and this is the output to the second logistic regression, right? So you can think of the second logistic regression as another linear classifier on top of this layer, right? So you should be able to imagine what's really happening is this right here. So the shape of so I'll actually have to remove this, and can I? Yeah. Okay. So right. So what's really happening is your two classes, your instances are actually warped into a latent space like this. So your space is warped. You can see that the space is being a little bit warped, right? The boundary is a little bit warped. And you can see that it's a little bit like kind of like S-shaped, like here, like this. So you can imagine that this model up here used a sigmoid activation function, because you can see that the space is warped a little bit like in an S shape, right? Like here, right? So your input space is warped into a latent space like this, and then after that, you can draw a linear decision boundary like this. Let me erase some of that. Like this. As I said, the second layer here is a linear classifier. It just so happens that the input to the second linear classifier has been warped like this, very friendly towards drawing a decision boundary and getting a perfect score. So that's what's happening. In the eye of the second linear classifier, everything is already linearly classifiable, or you can linearly separable. So that's here, this space, this warp space is what's happening here in the hidden layer, right? I mean, obviously this would be there will be two inputs, two hidden layers and one output, because this is a 2D space, right? This is a 2D space. But just you can imagine that's what's happening here. So how did this happen is how the power of hidden layer and how we can draw a non-linear decision boundary is actually just a chain of warping your space until it is linearly separable, so that the final linear classifier can draw a linear decision boundary and then get a perfect score. So that's what's happening here. So warping the space is like this. So what's happening here is just linear transformation. If you're familiar with linear algebra, then you can probably imagine what's happening here. So, well, actually, this part is nonlinear. So anything that has to do with expansion or compression or rotation or translation, like moving up and down, moving left to right, this is so far this is all linear transformation. But here, This is a nonlinear transformation, right? Because you're distorting the space with your choosing of any nonlinear activation function. It could be sigmoid function, it could be tanh function, it could be ReLU, PrelU, swish, any like nonlinear activation function. Based on that, your space will be warped like so. So here, expansion and rotation, translation. This is translation. Here, this is all linear transformation. And this is a linear transformation because you can see here, it's a little bit small, but here, your hidden layer is basically wx plus b with a nonlinear activation function. So up until here, everything is linear transformation. It could be expansion, rotation, compression, translation. It could be one of those, right? But this nonlinear activation function will distort your latent space, and then that's how you can get a final outcome like this, like this, and then your space, your two samples, your two classes are linearly separable. But without the nonlinear activation function, that wouldn't be possible. Like anything, if you just linearly expand them and then like rotate them, they wouldn't be linearly separable. You must have this nonlinear activation function. So all in all, what's happening to this well, we can start. Let's wait for the beginning. Yeah. In this case, this is such a let me see if I can. Yeah. I want to be able to actually stop them playing, but I'm not sure how I can do that. But you can see what's happening here. So the original image is like this, and then there are two classes that is never linearly separable. You can linearly separate them without actually severely distorting your latent space. Severely distorting your space. You need to like have them detach, decouple, um, like like this first class and this first class, they're so intertwined in a spiral-like manner, right? So you need to like detach, decouple them together. And the only way to do that is by severely warping or distorting your space like this, like this. This is what's happening. So if you have a chain of hidden layers, like there's layer 1, layer 2, layer 3, layer 4, layer 5, layer 6, layer 7, then you have a final output. That this is what happens when you go from one layer to the next layer, to the next layer, to the next layer, to the next layer, like this. So it's like, like pulling the space from like in a more like it's basically like you're pulling at each side from both like diagonally. That's the only way to have the red class and the blue class pull away from each other. So you're severely actually warping your space. So if you warp your space too much, then it'll probably overfit. So that's overfitting. You've warped your space too much to your training data that it wouldn't apply to a new unseen test data that well because your space is too like distorted. And it's gone overboard to fit to your training data and they get a perfect performance out of your training data. So you want to watch out and not do that. And even if you have all the layers in the world, like all the hidden layers, sometimes it's just not linearly separable. Like in an extreme case like this, you see what's happening here. They're so intertwined together, no matter how hard you try to like pull away, separate the two classes by warping your space more and more and more and more by using like more layers and more weird nonlinear activation functions. It's just not possible. It's just too intertwined, right? So that's what's happening in the latent space. So you can imagine with all the CNNs and RNNs and transformers, well, not exactly transformers are a little bit harder to imagine because it's using attention, but any multi-layer based neural network, what's happening inside is just warping the space until you can linearly separate the two classes. As long as you're talking about binary classification, that's what's happening. right. And this is a very informative example. So sometimes if your, how do I, yeah, if your input samples are completely unseparable, like for example here, well, sorry, yeah. For example here, you can somehow draw a nonlinear, sorry. So this is completely inseparable as given as it is. So for example, this extreme case like this here and here, you can still draw a very weird looking line. Like, let me see if I can change the color. Yeah, I can change the color. Like this. If you have a line like this, which would be weird, which would be a very weird looking decision boundary, but you can still draw a line to completely separate this guy from this guy, right? So it is doable. If you have like sufficient number of layers, then it is doable. But this guy, this is just impossible. You cannot draw a decision boundary. You have to draw it like this, but there's no way you can draw a decision boundary. Decision boundary always have to like be like this or this or like this, right? You can't have a decision boundary that looks like a circle, right? So the only way to actually, before we move on to the solution, we can see what's happening. If you try to learn train a latent space that can separate the red from the blue, it's just not going to happen. You can see it is struggling. Like no matter how many layers you throw into your model, it's just struggling, and your space is severely warped until it just collapses because it's not just separable at all. So you can imagine what you can do in this case, right? The problem is that you're trying to separate these two classes in the same dimension, in 2 dimension, which is not possible, which is impossible. So you need to actually use a higher dimensional space. You need one more axis. You need a 3-dimensional space in order to cleanly separate these two blue and red classes. So like like this. If you can just embed them into a higher dimensional space, then you can just simply separate this red thing. You can just lift the red thing and push down the blue things, and then it'll be linearly separable. You can think of having a hyperplane like this, where red ones are above the hyperplane, and the blue ones are below the hyperplane, like this, right? So this is the easiest solution. And sometimes that is why sometimes it's a good idea to put a little bit more extra nodes into the hidden layer instead of having so far what we've talked about is like in this example, it was just we're like keep using the same 2-dimensional space. Like we started from 2-dimensional input, and then we're using the 2-dimensional hidden layer again and again, again. So you can see that the space is actually retaining two dimensionality. Even though it's warped, it's still a 2 dimension, right? But here you're using actually 3 dimensions now. So this is one of the things that you can do. And it's the same goes with here as well. Yeah. Right. So any questions so far? I personally believe this is a very important concept, the latent space, how it is shaped, how it is warped, how they are trained by your objective function. So, and this gives you a very good idea. So, oh, there's a question. Would it still be viable to represent a complex data set to a lower dimensional latent space where the subtle details are important, or is this trade-off acceptable? If you're trying to embed a very high dimensional data into very low dimensional space, then you are going to lose a lot of details. But it depends on we're going to talk about that in the autoencoder actually. So it depends on what objective function you use. If you use an objective function that where the details are the most important features, then those details will survive in the latent space. But if your objective function is something, it doesn't have anything to do with the details of the high dimensional data, then they will all be lost while being projected into a smaller, lower dimensional space. So I would say it depends on your objective function. Okay, cool. Yeah. This is a very nice read, the whole blog. So if you have time, you can visit this later. Right. Any other question? All right, then we'll go back to the slide. All right. So here's the website, the URL. So if you have time, please visit there. So latent space, your latent space is shaped by your loss function. I've said this multiple times. Whether the smaller detail like granular detail survive or not, whether what kind of semantics you want your latent space to catch, such as mustache makeup in case of man and woman classification, it all depends on your loss function, your task basically. So for example, you've all done iris classification in the practice session, right? So in that case, if you use a multi-layer perceptron, then your latent space will be shaped in the way to maximize your classifier's performance to classify between different types of iris flowers, right? There was like iris like Veronica or something like I forgot the name anyway. Yeah. And this it all depends on your objective function. If you're trying to do French English translation, then your latent space will be shaped in a way that maximizes the translation performance of your model, which will be very hard to interpret, by the way. So yeah, today we're going to talk about image compression. So there are a lot of tasks, but autoencoder is basically about compression. So we're going to use image compression as a concrete example to build your autoencoders. Right, so autoencoder, it consists of encoder and decoder. So this is encoding, this is decoding. So in Korean that will be 암호화 복호화인가요? 그렇겠죠. So encoding and decoding. And in the same manner, you can also call it a compression and decompression. And we call this compression and decompression is because usually the space here in between is usually smaller than the original space here. So this is 784, but this is only 4, right? So you're compressing your original information into a lower dimensional space. So, and this is, you can also, some people call this like a code. Instead of like latent embedding or latent representation or hidden layer, you can call it a code because you're encoding and decoding. So it's like a transmission in the communication theory. Like it's can be seen as a transmission. So you're encoding and decoding, then basically in between this would be a code, but it's also latent variable, latent representation. They're all used interchangeably. Right, and basically, so there's an encoder and decoder. This is the most simplest example of autoencoder. You have just one layer, one nonlinear nonlinear transformation layer and one nonlinear transformation layer again. But this guy is this is 784, this is 784, and this is only 4, right? So you can imagine the dimensionality of this guy would be what? It would be 784 by 4. So it would be like a tall, thin matrix, and this B1 would be 4-dimension, right? So and also this nonlinear activation function could be anything of your choosing. It could be sigmoid, it could be tanh, it could be ReLU, it doesn't matter. But obviously we want to use a nonlinear activation function, as I said, because it gives you more power. It gives you the power to distort your latency, distort your space. Right. That's it. So all you need to do is to train your autoencoders to learn the parameters here, 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 and here. And typically we call the latent space Z. Sometimes people use H, but in this class I'll be using Z. So the encoding is basically you have your function, and you put your original image in the function, and then you'll get a 4-dimensional Z out. And your decoding will be putting your 4-dimensional Z in, and you'll get the original 784-dimensional output out. And what would be your loss function? Basically, what we want to do is we want to compress and decompress and retain as much information as possible. So we don't want to, we want the exact input. We want the output to look exactly like the input. So that would be autoencoder. That would be a proper compression. You don't want your zip file to lose information, right? So you can think of this as like zip file or something like basically compressing your information into four-dimensional space, which is a little bit extreme because the original was 784, and if you're pushing it down to 4, then that would be like 160 times. No, 100 something, like 180 times or something. So you're compressing it to a very extreme, but still you want to retain as much information as possible. So your loss function would be square derivative function. This is the most straightforward loss function. You want every single pixel values to be exactly the same. You want the first pixel value to be here, the second value pixel to be here, this to look like this to look like this. So every single pixel you want to be the same. So that's why you use a square derivative function like this. And that's it. Then you just plug in, you just type in these functions, and you just set this loss function. You just set the loss function to the MSE function or the mean square derivative function, and then you start back propagating, and then you have your autoencoder, and that's it. A very simple architecture, right? Sometimes you can use multiple hidden layers before you get to Z. So you throw in like one H between X and Z, and another H prime in between Z and X prime, right? And then that'll add more power to your autoencoder because you have one more chance to additionally distort your space before getting to the final code, right? So it's kind of like you have more. So the number of hidden layers you throw into your model will decide how many distortions or warpings you get to do with your space before you get to the final output. So here, yeah, you just add one more layer. Then you would have 1, 2, 3, 4 matrices and 1, 2, 3, 4 biases to learn. So obviously there's more things to learn. And how, so this kind of like boils down to whose question was it? Was it Namo's question? Yeah, Namo's question about what can we like retain detailed information into this part, the latent space. And this latent space works as an information bottleneck. So because we set the dimensionality of our Z into a 4-dimensional, or it could be anything but smaller dimension than the original dimension. This was 784 and this is 4, but it could be 16, 20, 24. Still, it's a bottleneck. You have for example, you can think of like a water pipe like this, right? So if you have water flowing in, then this is your bottleneck, right? Bottleneck. So it's kind of same analogy. You have information flowing in, and this is severe bottleneck, and then you have another if you have information flowing out. So on a high level, like qualitatively speaking, only the most important information will be saved here. Because you have no other, you don't have like leeway. You don't have the space to remember all the unnecessary information about your input because your space is too small here. You only retain the most important features from your original space, and all the other things are actually thrown out. So you, just like it says, need to pack all information in 4D. So the most useful hidden features only. And what are the most useful hidden features in our case? What will be remembered in this 4-dimensional space in our example? Remember that our example is autoencoder, whose objective function is this, right? So whatever information that is retained in the latent space will be the ones that that minimizes this error, or that maximizes the retention of the keeping the same image before and after the compression decompression, right? So that is what will be learned. That is how we define useful in this case. I mean, useful features can differ based on what task you're doing, whether you're doing translation, image generation, or LLM. There are a lot of different tasks. But in our specific case, which is compression and decompression, then useful means whatever features that is useful for compressing and decompressing and retaining as much information as possible, right? So far, so good. 혹시 질문 있으신가요, 여기까지? I'm keep exaggerating this because this will lead to something a relationship between autoencoders and PCAs actually. So I'm asking a question here. Still, would this four-dimensional space still consist of the four axes that we used in the previous slide, which is like long hair, mustache, ribbon, makeup? Like, if you remember what these features were for, then probably this latent space will no longer capture these information because these information were learned, these features were learned based on the task, which is man and woman classification. But that is no longer our task. Our task is compression and decompression. It's not man or woman classification, right? So this latent space will no longer have anything to do with these, right? I mean, they still might be useful for like, like keeping information between before and after the compression decompression, right? But um, I'm just trying to say that here these features were derived from the man and woman classification, and that is not what we're doing. So probably not. We're trying to think about this in terms of like PCA. PCA is kind of like a compression algorithm. You want to project your original information into a lower dimensional space by having a principal by finding the principal components, right? I hope that everybody here already has basic understandings of PCA. So let's go into a head-to-head comparison between autoencoders and PCAs. So PCA, again, it minimizes reconstruction error, which is the same as maximizing variance between samples. So this here, if your original information or samples look like this, then your principal components would look like this and this. And the reason that we use this as a principal component is because this axis is the best axis in distinguishing all the different features. Because if you use this axis, then a lot of the features here remain in the same spot. If you use if this is your let me blow it up and draw it. If you use this as an axis, then there's like, let's call this like new x-axis, like x1. Then this will be your values, and you can see a lot of dots belong to the same value. So you lose distinguishability between samples. So it's better to actually use this axis. Let's call this x2, because on here there are different values, and you can see fewer samples belong to the same value. So you have more distinguishability between samples compared to x1. So that is why these become the principal components. And it's kind of like the same here, same analogy. So if you go here, you're maximizing the variance. So the variance being you want to see more varied samples by using a new axis. But this boils down to linear transformation. And what you do is you select k variance maximizing bases, which we call principal components. So if your original space is like 784, then you can choose to use top 10 principal components, top 100 principal components, or top 200 principal components. It all depends on your preference. And if you want to use like higher dimension, then you can use kernel tricks to embed your information into a higher dimension. Compared to that, autoencoders, again, it's minimizing reconstruction error. It was exactly that. You can see here, it was minimizing the reconstruction error, right? So, but that again boils down to maximizing the variance. Because when you say that you want to minimize reconstruction error, you have a bottleneck here. And as I said, only the most useful features will be retained in this space. And that useful feature, it happens to be the one that most distinguishes each sample by sample. So let me draw an example here. Let's say that all your samples into this input is a portrait. It's a human face. So sometimes they will all look like this, more or less. And let's assume that their background is all black. This is all black, all black. They just have like all the people happen to take their portraits from the same studio, same 사진관, right? So, but some people have like glasses on. Some people have mustache. Some people have like long hair. And some people have, like, I don't know. Let's say some people have like necklace. Like, yeah, this is a little bit weird. Then what are the distinguishing properties or features of these samples? Because all the shapes are pretty much the same. They all have head, they all have like shoulder, and they all have black background, and they're all the same size. And those information are not necessary for maximizing the reconstruction because all these unchanging, unvarying, basically low variance features can be stored in here because you can just memorize them because every single portrait or every single sample have a low variance features, which are the background, the shape, and like those kind of things. Like they all have like eyes and nose and ears and mouths, and they all have shoulders, they all have neck. They are unvarying or low variance features, so they can all be memorized into these parameters. The only ones that distinguish one sample from another or the high variance features are such as glasses, mustache, long hair, or necklace. These are the ones that separate one sample from another, right? So those are the information that will be stored in here. You put this in, then this will retain, oh, this guy has glasses on, so I'll have like put this up here. Like I'll like dial up the feature values here. Oh, this guy has like long hair, then oh, I'll dial down this feature here. Oh, this guy has like accessories, then oh, I'll dial up the features here. Something like that, basically. Like this is what would imagine. You can imagine this kind of things will happen inside the latent space, and that would be high variance features being memorized or being embedded into the latent space. And that is why these two are so similar, because PCA goes for high variance axes, high K variance maximizing bases, or we call them principal components. Here, autoencoder, we try to learn a latent space which retains high variance information. But this one happens to be linear transformation. This happens to be linear transformation. And you define how many nodes you want to use. Basically, there was 4 here. How many nodes you want to use in the latent space beforehand, before you start training your models. As opposed to PCA, where you can post hoc choose the K principal components. And you can easily map it to a higher dimensional space because you can just set this to be 1000 or 2000 based on your preference. So this is the relationship between PCA and autoencoder. Basically, they're doing the same. It's when you say you want to maximize reconstruction performance, it boils down to memorizing high variance features. Right. So in that case, you can imagine what would happen if you use a higher dimensional latent space than your input space. If your input space is 784 and this 1000, what would happen? If DIMZ was higher than DIMX, then you can just, can you imagine what would happen? I mean, this is no longer a compression because there is no bottleneck here. This is actually, this pipe, I mean, this segment of the entire pipe is actually wider than your input and output. So there's nothing to lose. Can store all information. Exactly. You can actually just have this part be identity function. You can just map this exactly to this part and then map it exactly to that part, like here. So you're not losing anything. So this is not actually achieving our initial motivation, which was compressing and then retaining the most high varying features. This doesn't have to do any of that because there's no bottleneck here. Question from Hung Bin. Then how do we decide the optimal number of features to retain the most important information? That's a good question, and that is usually we don't know. it depends on what you want to do in the downstream task. The reason that you want to compress your information is so that you can save your memory or save your hard disk space or whatever. Like you're basically saving space. So, and based on that, you want to do something, right? Like saving space is not the end goal. You have an end goal. You want to maybe build a classifier based on that, or you want to do some other like interesting stuff. So based on what you want to do next decides how much space you want to save. Like if you try to save too much space, then you can, for example, push it down to 2 dimension, but that would just, that would be too extreme. So you want to like do a moderate amount of compression so that your downstream test can retain, like achieve some level of good performance, right? So what number is that? What number should this be? That depends on your downstream task. Hope that answers your question. Like nothing is really like fixed in stone. Like it's all like depends on your how much resource you have, how much time you have, how much like compute you have, how much performance you need to achieve. Like all it depends all on like those constraints. Right. So yeah, as Junsung said, you can store all information in this type of autoencoder, which would be uninteresting. Like why would you do this anyway? So training process, I think we can just go over the high level ideas and then go to the more interesting stuff. So you will get to this. I think you've already done this in the previous practice session, but in training neural networks, you basically have a train and validation test set. You have 3 sets. And you need the validation set to do an early stopping so that you can stop your model prevent your model being overfit to your training data. So what you do is you have a training, validation, and test set. And obviously you want to start with a loading of data, then defining a model M. You need to implement a model. In this case, it would be an image compression model, an autoencoder model. Defining a loss. In this case, we used a MSE loss, the squared error loss. And you have to define an optimizer, which could be ADAM optimizer, it could be gradient descent, it could be anything, anything of your preference. Then you have a training loop, and then you evaluate your best model on this test set. So this will be done only once. Using a test set is done only once after you've finished your training phase. And during the training phase, you will sometimes use validation set to see how much your model is how good your model is doing to an unseen validation set. Right? So yeah, we'll skip the details. I mean, splitting the data set, you can easily use like sklearn's train test split, and it could be 811, 622. It depends on your preference, depends on your task. And loading the data, you can fit your entire data. If your data is small enough, you can fit your entire data into the memory, or if it's not, you'll need to stream from your disk, which would be a little bit more work, but there are no other choice. For example, if you're training LLMs using like 5 something terabytes of 5, no, yeah, I forgot, like how large, 5 tera, not bytes, I, like 5 trillion tokens or something. Like it would be humongous basically, and it would never fit in your memory. In that case, it would have to be streamed from disk, and you'll need to properly set up the streaming of the disk. And yeah, define a model. You can define your own. You can implement your own model using like TorchNN. But in practice sessions, you will be doing this. But in reality, when you're using like transformers, you most likely just call models from like Hugging Face. And then you choose your optimizer. It could be SGD, like vanilla SGD. It could be AdaGrad, ADAM, ADAMX. There's like a lot of different optimizers out there. So if you're into those kind of things, you can study which optimizers have like the pros and cons of each optimizer, or yeah, each optimizer, and then choose whatever, uh, to your heart's content. Yeah. And the training loop itself is pretty straightforward. Basically, we're going for a mini batch based gradient descent, right? So it's mini batch based update. So you have epoch, which is going through the entire training set once. That is 1 epoch. If you do another run on your entire training set, that is 2 epochs, 3 epochs, 4 epochs, and each epoch consists of multiple mini batches. So let's say that you have let's say that you have like size 16 mini batch. And so let's say that your entire training set consists of 1,000 samples, and your mini batch is like 10 size, 10 sample mini batch. Then you need to run this how many times? 100 times. You need to run 100 iterations to cover the entire training set, and that would be your one epoch. If you do it again, then that's 2 epochs, and 3 epochs, and 4 epochs, and so on and so forth, right? So each time you use a mini batch of samples, then you use that to calculate the gradients, and then calculate your loss function, then calculate the gradients, and then you update your model's parameters. Then you go to the next batch, and then the next batch, and then the next batch, and then the next batch. And if you do it for 100 times, you will have covered the entire training set once. And from time to time, you want to evaluate your model performance on validation set from time to time. Like every epoch, or maybe every 10 mini batches, or every 100 mini batches, or even like every 1 mini batch, if that's what you want. Like every so often on a regular period, you want to evaluate how your model is doing on the validation set. And if your validation performance starts to decrease, then that's a good place to stop your model from training. Right. I'll just skip the details. You'll see what these are about in this week's, or probably like last week's practice session and this week's practice session. You'll be using this a lot, like data loader and these types of stuff. Important thing is actually, yeah, I'll want to just note on this. When you update your model's parameter using whatever optimization algorithm of your choosing, you first need to flush out the gradients from your previous mini batch. So you run your mini batch like n number of times, right? 100 number of times in our concrete example. So each time you move on from one mini batch to another, you need to flush out the gradient information from the previous mini batch so that you can get a fresh start, and then call the backward, which is the back propagation, to calculate all the like the gradient, the activation values. The gradient values from all the layers, and then update, which is the step, which is to actually update your parameters from all the layers. Hopefully you understand. You can imagine what's happening. If you can think of the image from the previous class, the lecture number 3, where we talked about the back propagation algorithm, this is what happens there. Backward is calculating from top to the bottom, all the gradient values based on the activation values that you saved during your forward propagation. Based on that, you go from top to bottom to get the gradient values. And then based on the gradient values, you do a step, which is updating your parameters everywhere from top to bottom to top. Right. So I'll skip the validation, getting the validation performance and saving the models and whatnot. Yeah. Right. So let's go to the visualization. So once you've compressed your information into a lower dimensional space, you would probably want to see what it looks like, right? So this is already visible. This is a 784, like 28 by 28 pixel value. It could be like PNG or JPEG or whatever, right? So this is already visible, but if you embed it into a lower dimensional space, you probably can't really imagine what kind of values these are. And what you can imagine is just, like if it's the same, like digit 1, then their latent values would be more similar than versus like 1, 1, and 5. Like these are all ones, so you can imagine they will be mapped to or compressed to a similar values compared to 5 being compressed into a 4-dimensional space. But you would actually like to see if that's true, right? If you would like to see that if all the ones are mapped to the similar values, and if all the 5s are mapped to similar values, and 1s and 5s are like residing, like they live in a different place in the latent space. Like you would like to see that. But if it's 4-dimensional, then it's hard to see because we cannot understand 4 dimensions. So obviously you want to map them into 2-dimensional space so that you can scatter plot them, right? Like kind of like this. Like all the 1s live here, all the 3s live here, all the 2s live here. But sometimes they're like all like mixed together, like 7, 5, 4. They live in the same neighborhood, unfortunately. And 0 and 3, 7 again. Don't know why. Like this probably wasn't a very good compression algorithm. But anyway, it's easier to draw on the 2D plane. So let's assume that what you really wanted to do was compress your image into 4-dimensional space. So you're going to use this 4-dimensional embeddings later down in the downstream tasks, such as classification or clustering or whatever. But at the moment, after you've trained your compression algorithm, at the moment, you would like to see if your compression algorithm is doing a good job. So in that particular moment, you need to further compress them into 2-dimensional space. So just so you can scatter plot them. You're not going to use that two-dimensional output for downstream tasks like clustering. You're going to do that with these values. But just for visualization, you want to compress them into 2-dimensional space so you can see things like this. So what you can do is from dim-z to 2, so 4 to 2, and so that we can scatter plot in 2D plane. That's it. That's all we want to do with the 2-dimensional outputs. And there are 3 popular algorithms, as long as I can remember it, which is PCA, t-SNE, and UMAP. So these are kind of the algorithms that a lot of people use just for visualization purposes and nothing else. And especially these two, like t-SNE and UMAP. PCA, sometimes we use them for, actual information compression and then use that for downstream tasks. But these two, I don't think I've ever seen anyone use these two for compression purposes. These are for like visualization purposes. So let's get on to that. So PCA is, as you already know, it's variance space. So you're trying to look for the high variance principal components, axes, and that's already in scikit-learn, so you can easily call them. t-SNE is distance space. So distance space meaning if 2 samples were similar in the original space, then they're in the latent space, they will still be side by side. They will still live very close to each other. If 2 samples were far away from each other in the original space, such as like 1 and 5, then their latent space embeddings would also live far away from each other. So you're trying to preserve the distance in the original space to the latent space. So that's why we call it distance space. And it also is also in scikit-learn. UMAP is a little bit more, well, I don't know the exact algorithm, but people say that, the authors and a lot of people say that UMAP preserves the global structure of the samples a little bit better than t-SNE, because in t-SNE, the distance, like sample-wise distance, are pretty much well preserved, but the global structure is not well preserved. So we'll get to that. Anyway, so UMAP is a little bit more advanced than t-SNE. So I would say it's a little bit, there's no reason not to use UMAP as opposed to t-SNE, but there's a little bit caveat, which is, yeah, it's not in scikit-learn. t-SNE is in scikit-learn, so you can just call the API. But UMAP, you need to actually install the UMAP library and hook it up to scikit-learn somehow. It's a little bit more cumbersome in the beginning. But as long as you've installed it, then you can just call the API. So it's just a little bit of overhead. Right. So we can actually, I'd like to show you again example of the comparison between t-SNE and UMAP. I'll just go to this website real quick. Yep, right here. So this left side is UMAP and right side is t-SNE. And what this is a compression of images of different clothes. I think this is, yeah, Fashion MNIST. This is Fashion MNIST. So they're all basically just some like clothes, like t-shirts and handbags and like sneakers and sandals, like sandals. Yeah. So they're like t-shirt, shirt, pullover, coat, dress, sandals, like sneaker, ankle boot, trouser bag, and whatnot. And you can see that UMAP is a little bit more like separated between different classes of samples, like all the like footwear, like ankle boots, sandals, sneakers. Sneakers. They're all in like one side of the space, And the other one, what are these? These are like pants. So pants, like trousers, are on the way over the other side of the latent space. And what are these? Yeah, it's not so easy. Yeah. Anyway, you can see what I'm trying to say. Like different classes of like um like items are in like they have their own space. They have their own neighborhood in the latent space. As opposed to T-SNE. T-SNE is a little bit, I mean, they're still like well clustered. You can see the trousers are all here. Trousers are all here. Sneakers are all here. And in the vicinity, there's like sandal here and ankle boot here. So it's relatively okay. I mean, if you think, I mean, unfortunately, we don't have a PCA here, but if you compare to other like compression algorithms, this is still like okay. You can see that like similar items are embedded into a similar lower dimensional space, but UMAP is way more like clearer. So that's the yeah strength of UMAP. But still, like UMAP teasing is like it's doing its job just fine. Is if you just want to have the global structure retained, then UMAP is the one to go. All right, so back to the slides again. So as I said, these two are for visualization purposes. Please don't use T-SNE or UMAP for compression and then use it for downstream testing. I mean, some people might have done it. I don't know, like, but I haven't seen any paper that do that, right? Okay, so I think we have just enough time to cover autoencoder variants real quick. So far, we've talked about just the vanilla autoencoder. And we had this example here where it was actually the latent space was larger than the input space, which would serve no purpose, as someone said, like, because you can entirely memorize the entire thing, and that would beat the purpose of having an autoencoder in the beginning, right? But if you can somehow induce sparsity inside the latent space, then that's a different story. So induce sparse latent representation for better performance on downstream classifications. You can think of it like a dropout. You have a series of hidden layers, and some hidden layers will be wider than your input. If, for example, if your input space is like 784, then and you have 1,000 nodes in your hidden space, then that would be like having a higher dimension. But then you would use dropout on your hidden layer, so that sometimes your nodes will be deactivated, right? Kind of like the same thing. You're deactivating your latent space dimensions, some portion of your latent space dimensions to 0, so that only like these will be activated. And that's kind of like inducing sparse representation. And that would be hopefully just like how dropout gives you a robust model, this will also give you a robust autoencoder, a compression algorithm. That's the high level idea. So how do we induce sparsity? So the loss function would be twofold. So there's the original reconstruction loss, the MSE loss, and there's a sparsity inducing term, omega, here. So you want to have one more loss term that will somehow penalize too many values, too many dimensions being activated. You want to penalize that so that only a few dimensions will be activated at a time. So what kind of sparsity inducing terms can we use? There are, well, I mean, there are a lot of, you can have like infinite ideas, but basically you have one which is KL based, so KL divergence, which is you have a target Bernoulli distribution mean. So for example, you want all the dimensions to be activated 10% of the time, then you can have a target row to be 0.1, 0.1, oops, 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, 0.1. So this would be your target vector. So you plug that here, and then you have your average z's plugged in here, and then you want to minimize the gap between the two using KL divergence, right? So that's it. You want your average activation probability, should I say, probability of z to be 10%, all the way 10%. So that's how you use KL divergence. Another is just simple, let's just erase this. Another one is just simple L1 regularization. I've talked about L1 regularization in the second video, I think. In the second video is a little bit longer because I talk about like L1 and L2 regularization and how they are like if L1 is like a diamond-shaped regularization field and like L2 is like a concentric circle shaped regularization and L1 because of the diamond-shaped thing it induces sparsity. So it's the same thing. You use L1 regularization as the loss term here to induce sparsity. Right. So that's sparse autoencoder. But I haven't seen a lot of people use sparse autoencoder. Actually, I've never seen. Well, I mean, there are infinite number of papers out there, so somebody might be using sparse autoencoders today. But in my experience, personally, I've never seen any work that uses sparse. But then again, I'm an application researcher. I'm not a theory researcher. So who am I to say? But anyway, not a very popular algorithm. I think that much is true. Another one is denoising autoencoder, which is again another variant of autoencoder, and it's again this is kind of like uh, if you guys are like familiar with computer vision, then we do a lot of augmentation, right? When you do contrastive learning, you augment two views of images using like solarization or like cut or rotation or like Gaussian noise or blur or something like that, right? You can think of denoising autoencoders like that. You want to add some amount of small noise into your original image and then reconstruct the original image so that your model can ignore these small noises. So you want your model to be robust to a small amount of noise, right? So small noise, the high level idea is small amount of noise doesn't affect high level representation. So just because there are some like dots here, it doesn't destroy the whole semantic, which is that it is a digit two, right? So as long as small noise, then you can probably train your model to like remove all the noises and then reconstruct the original like clean image digit two. So that's the high level idea. And also in order to do this, in order to do denoising, autoencoder must learn useful patterns. Useful pattern meaning the ones that really matter, the high variance patterns. High variance pattern. If you add small amount of noise to all the digits, then they become low variance features because all images contain these small dots, right? So they are everywhere in all samples, meaning they are low variance, low distinguishability features. So your model in your latent space, they will not remember these, right? They'll only remember the ones that survive the noises, like the large 2 or large 1, large 5, large 7, large 9, like those important features. So that's the whole idea. Yeah. Yeah, reminds you of something, it would be PCA. Because you're only retaining high variance features and small amount of noise that is everywhere in all the samples. They're low variance features, so you don't care about them. They will be low priority principal component. So how do we train it? So the loss function is input. You have to be careful. The loss function is not this. You're not reconstructing the noise-ridden, noise-strewn image. You're actually reconstructing the original ones. That if you do this, then you're actually beating the purpose of trying not to remember all the small itty bitty detailed noise in the latent space. If you do this, then your latent space will try to remember all the noises, right? So you don't want that happening. So you need this. You want, even though your input to your autoencoder is noise ridden, you want your original clean image to be reconstructed so that your latent space will not focus on the small amount of noise. And corruption usually is Gaussian noise. So this is kind of like how very similar to contrastive learning, like the SimClear, because in SimClear you want two images of the same semantics. It could be same dog, but one has like a Gaussian blur and another has like Gaussian noise. You want those small amount of noise or small amount of like distractors to be forgotten in the latent space. You only want the model to focus on the important information, which is that it's a dog image. All the small itty bitty details or small blur, small smudge, small rotation, small cut doesn't really matter as long as it's a dog, right? So it's the same spirit, But again, I don't see a lot of people. Actually, autoencoder itself is not a very popular algorithm anyway. So, and not needless to say, denoising or like sparse autoencoders, they are not very like widely used. But it's good to like, like remember the core ideas and why sparsity or denoising process um, improves the performance of latent space learning, which is to retain the high level semantics and forget about like small amount of noise. Okay, I think this is it. So yeah, this is the end of the class. And any question before we end the class? Again, as I said, I'm a little bit concerned that we skipped two lecture sessions, even from I mean, the very beginning, the very fundamental knowledge, fundamental lectures. So I'm kind of worried that if today's lecture makes like total 100% sense to all of you. So if you have any question, um, you can. Yeah, I hope that everybody at least watch the video because as long as you watch the video, you're on course, you're on track. Question. Actually, I'm interested in contrast learning, self-supervised learning, and this is an off-topic question. Where would you recommend studying this topic more, like online notebooks? Uh, yeah, I would suggest there are like tons of like blogs or like tutorials out there. Um, Contrastive learning is I would start with SimClear. So contrastive learning itself is a theory, but a concrete implementation of contrast learning is SimClear, and I find it always useful to start with a concrete application or concrete implementation because I'm not a theory guy. If you're a theory guy, you're probably more interested in the theory itself, but I'm an application guy. So I'm interested in how theories can be applied to real problems, right? So if you start with SimClear, I think that's a good start. Okay, cool. So the class is over. So if you don't have any question, you can, feel free to leave. If you do have question, I'll stick around for like 10 or 20 seconds more, just in case you're typing. Okay, I think there are no more questions. All right. Thank you guys then. I'll see you guys next week. Thank you. Bye-bye. 네, thank you. 네, 감사합니다.